In considering moments and center of mass here, we're going to start with a one-dimensional case. And in the one-dimensional case, this is based on the law of the lever. So we've got our axis here, and we have a couple of weights attached to that. So right here, we've got a weight of mass m1. And over here we've got another weight of mass m2. And then we've got a fulcrum in the middle here, right here. And then we want to put a scale on this axis here. So we could say 0 starts here, and this is going to be our positive x-axis. Then the coordinate of this fulcrum here, let's put a dotted line in there. We want to find the coordinate of that fulcrum. And what we know is that if you look at the distance from the fulcrum, the balance point here, that's d1, and then look at the distance from the fulcrum to the mass m2, we'll call that d2. Law of the lever says that m1 d1 has to equal m2 d2. So if your mass increases here, your distance is going to decrease. If mass decreases, your distance has to increase. And if you ever used a teeter-totter when you were a kid, you kind of know that if your dad is sitting on the other end, then he sits closer to the fulcrum, to the balance point, and you sit way out on the end so that you guys can balance. So we have some practical experience with law of the lever. It's the teeter-totter law. So if we put coordinates on here, so set the fulcrum at the coordinate x bar, and then let's set mass 1 at coordinate x1, and then mass 2 at coordinate x2. Then the law of the lever, this distance d1 is going to be x1 minus x bar, right minus left, x bar minus x1 here. And then distance d2 is x2 minus x bar, right minus left here. And then we can multiply these guys out. And we get m1 x bar minus m1 x1 is m2 x2 minus m2 x bar. So that's just distributive property. And now we're going to collect our x bar terms on the left-hand side. So bring this guy over as a positive. Right here it is. And then bring this over on the right as a positive. And right here it is. And then notice here we've got x bar as a common factor. We factored that out in front here. m1 is left here, plus m2 is left here. And then we want to divide this m1 plus m2 off of both sides. Right here it is. So it'll cancel on the left, and we're left with m1 x1 plus m2 x2 over m1 plus m2. So we can generalize, this is our equation for the fulcrum, the balance point, the x-coordinate of the fulcrum. This is just for 2 masses, but we can generalize that for n masses. You sum up the mass times the coordinate at which that mass is situated, and then divide by the sum of the masses, which is the total mass in the system. So, and that'll give our coordinate of the balance point. So let's go ahead and put this to work. So here we've got some masses, 35 grams at a coordinate of -3, 20 grams at -2, 15 at +1, and then 20 at +5. And we want to find the center of mass. We want to find the coordinate of that balance point. So it looks like that, maybe should be somewhere in here, possibly, because you've got some heavier masses here, and you've got some lighter ones over there, so it should probably be closer to the heavier masses. So I'm just kind of eyeballing. But let's go ahead and apply our formula here. So our x bar should be, our balance point coordinate should be, we're going to sum the mass times the coordinate. So we've got 35 grams at coordinate -3, and then plus 20 grams at -2, and then plus 15 at 1, so 15 times 1, and then 20 grams out at 5. And then we are dividing by the total mass in the system, 35 plus 20 plus 15 plus 20. And if you plug this into the calculator, you will get negative 30 on the top and then a total mass of 90 on the bottom, which reduces to negative 1/3. So then that's about right where I've got that. So this coordinate here is negative 1/3 on the x-axis, and that is indeed our fulcrum, our balance point for that system.